Right, hello, this is, I'm going to talk about this particular exam here. A-Level Further Maths, 2022. Hopefully it'll, nevertheless it'll be useful for people who didn't actually take the exam in general. If you're unaware of what the A-Level is, I mean, this A-Level Further Mathematics, it's probably covers a lot of the mathematics that people will, well, not a lot, but it covers mathematics that people will tend to do in the first year of a university course, although people actually take A-levels when they're actually 18, when they're still at school. I've got a website down there, www.maca.co.uk. On there you'll be able to get full worked examples for this particular exam and others, and it'll also have links to the exam paper itself, although the exam paper itself is subject to copyright if it's quite recent. So I intend just to talk about one or two points working through this exam. I don't intend to give a comprehensive account of all the questions. So the first question was this one here. I don't know, can you see that probably? Obviously you can freeze this on frame, so I won't keep it too long. The important thing here, I mean, there's one or two things to say about this. On the line 1, there's a minus. There should be a minus sign included, which that has been omitted. Line 4 is the important one. I can just mention in passing. It talks about argument Z1 over Z2. That doesn't carry through as a division. It becomes arg Z1 minus arg Z2. Sorry, arg Z2. As you were, arg Z1 minus arg Z2. I mean, this is very much in line with the way that you deal with multiplication and division of complex numbers in general. You multiply two complex numbers together, then you actually add the angles, and vice versa for division. Right, this one. Mathematical induction. This right. The way I'd start is write down, say, okay, assume for n equals k, and then you have mk equals 3k a over 2 3k minus 1. Okay, so I'm saying it's assume, oh sorry, I should say assume true. Okay, a lot of people are quite loose on this and say n equals k and then they put this down, but the real rigorous way to do it is to say assume this is true for n equals k, and then you'd say then for n equals k plus 1. Right, now you know what you're trying to achieve here. You're trying to manipulate things so that you get this with all the k's substituted by k plus 1. Now in something like this, what you do first of all for an induction of this type is you say, okay, mk plus 1. What you do is you just stick down what you've got down already, m3k a over 2 . And then you actually add, you've got the m at the top there, so you actually multiply it by that, m3a. Okay, so you're taking m of k, m to the power k, and you're just multiplying it through by another m to get mk plus 1. And you follow that through, and hopefully, as I say, you know what you're going to get. You want this expression just with all the k's substituted with a k plus 1. One thing you've got to be careful here is that because you know what you're going to get, you need to show your full procedure. There's a bit of a nasty bit of arithmetic on this top right one. So you don't just what I'm saying is that you stick down every step to show that you have actually derived the expression at the end. You're going to have this, with just that being k plus 1 instead of just k. But you don't just write that down, because you obviously know what you're going to get. You need to show the examiner that you actually have derived it properly. So you need to put each step in. And I mean, I could go on forever on things like this. One thing that not disturbing, quite off-putting at times, is that some people tend to. I mean, you could actually. Some people do strangely start at the end and work through to the beginning. But what's off-putting at times is people start off at the beginning, find they can't go anywhere, and they go to the back, and then they work backwards, and they somehow meet in the middle. Which is not the way to do it. You need to start off just at one end and work right through to the end. If you want to be perverse and start from the end and go forwards, that would be okay as well. But don't mix the things. So what you need to do once you've proven that, once you've got your expression, you've got a situation where you assume that it's true for n equals k. Therefore, you've shown that it's true for n equals k plus 1. But you need to show that it's true for one specific case in order for the whole thing to work. So you can say, okay, let n equals 1. So you can equate that again, but you need to show a bit of working here. You can say, okay, in that expression there, you can say, okay, write it down as a over 2, 3 minus 1 equals 2, and so on. Just do a bit of arithmetic there to show you've actually done a bit of work on it. Otherwise, you're going to lose the marks. And somewhere along the lines here, you need to include put in a conclusion, which normally sometimes the expressions you put down in here do suffice, but the conclusion would be, to me, it would be 2 sentences. The first sentence would be, we've assumed that it's true for n equals k, and thereby proved that it's true for n equals k plus 1. I mean, that's the core of what you've done. You've assumed that if it's true for n equals k, it's then true for n equals k plus 1. And then you can add a second sentence. There, we've proved it's true for n equals 1, therefore it's true for all n, or for all positive integers, something like that. But that does need to be put in for the full marks. Now this second bit, the triangle T is transformed to triangle T bar by the transformation represented by m to the power n. So if I can do it schematically, T1 equals n T. So these are matrices. Now the thing is that this will act as a magnification factor. The size of this triangle, the size of the triangle represented by this matrix, will be increased by the determinant of this this matrix here. So we're told that it's T dash is 1, 2, 1, 5, and initially T has got an area of 5. So dividing one by the other, the actual multiplier factor is 2, 4, 3. I think it's 2, 4, 3. So what I'm saying is that the determinant of this matrix will equal 2, 4, 3. Now, so mn equals 2, 4, 3. Now, you need to realise that mn equals mn. And the magnitude of m, there's m at the top there. The determinant of this equals 3. You can see that from that. So that will be equal to 3 to the power n. So I've got 2, 4, 3 equals 3n, which will give me n equals 5. So that's the answer for n. A, you need to refer back to the original matrix. A is up here. So you can set up in a matrix equation to work out what A is. But this is the fundamental principles you need for the first bit. Now this first bit here, number 1, what you're going to do is to decompose each of these into a more basic form and then add. For example, here you've got that 6e to the power of pi over 3. You can reduce that to 6 cosine pi over 3 plus I sine pi over 3. You can reduce that down to numbers. Do the same for z2. Add them together and then work backwards to prove that. The second part was a bit more caused a bit more problems. Arg z minus 5 equals 2 pi over 3. Now these arguments, as we've come across these in the first question. I mean, essentially the arguments delineate more or less the well, you can imagine a sort of a coordinate system of r and theta. The magnitude of z equals constant would sort of delineate the circles, which would correspond to the coordinate lines for r, if you like, whereas the arg will delineate the coordinate lines for the angles. So we've got if it was arg z equals 2 pi over 3, that would be something like that. That would be 2 pi over 3. What we've got here is arg z minus 5, 2 pi over 3. So what will happen is it will move, that'll be 5, sorry, give me a line. Okay, so it's just, see what I've done? Arg z minus 5, so just taken arg z and just translated it 5 units to the right. So that's 2 pi over 3. So that's so that one is pi over 3. Now it says determine the least value of the magnitude of z as z varies. So what that means is that this z is going to start from here, but it's going to vary. It's going to vary, or the magnitude of z is going to vary as z sweeps along this line here. Now, where it's going to have its least value is where it crosses or it encounters this line here at a right angle. So that's basically pretty straightforward from there. You need to work out the magnitude of this line. So we know that the sine of pi over 3 equals magnitude of z over 5. Then you go from there, leading to the magnitude of z equals 5 root 3 over 2. This starts off fairly straightforwardly. I mean, there's a couple of ways of doing this. Kind of y equals arc sine x. Now you need to prove this here. So you could say that x equals sine y. So yeah, you could do that differentiate that implicitly, or you could just say dx over dy equals cosine y, which equals 1 minus sine squared y. And sine y equals x, so that just equals 1 over. Finally, just turn it over, 1 x squared. The second part caused a bit more problems. First thing to notice is that some people thought the derivative of this was 1 over the square root of 1 minus x squared, which is that's obviously not. It's well, dy by dx of this is 1 over. It's not x. It's 1 over x squared, but it's a function of function here. So you need to say, okay, times the derivative of that, so it's times ex. Okay, so in the olden days you might have worked this through by a substitution. You might have said, okay, let u equals e to the power x, du by dx equals e to the power x, and done then a sort of function by function thing. But I'm just doing it straight off, as long as you're happy with the original idea. So the question now says, show that f of x has no stationary points. So having got the derivative, some people made a bit of a meal of this. You just need to state that e of x is never 0. Therefore, since dy by dx is never 0, there are no stationary points. I mean, very, very rough sketch of what e to the power x is something like this. Or you could just state that e to the power x, e to the power x is never equal to 0. Therefore, dy by dx is never equal to 0, and therefore there are no stationary points. But you do need to make that full statement. You can't just show that dy by dx equals 0. You and I might know that's actually shown the statement, but you need to show it explicitly, i.e. you need to show explicitly that dy by dx equals 0 is the requirement for stationary points. I mean, this might seem a bit pedantic saying this, but it happens quite frequently actually in A-levels. Off the top of my head, the best example is when you're trying to use the factor theorem. You might be given a polynomial and you say, okay, show that x minus 2 is a factor. And some people, given a question like that, will just steam ahead and say, okay, f to the 2 equals such and such, which equals 0, and leave it at that. But you've lost points there because, like here, you haven't actually shown explicitly that x minus 2 is a factor. You need to insert something in there to say, okay, if x minus 2 is a factor, then f to the 2 equals 0. And then you can plough ahead and find out f of 2 equals 0, and thus get full marks. Right. Polar coordinates. Now what you're doing for the first part, you need to show the polar coordinates a are 2 pi over 4. What you're actually doing is you're taking the traditional sort of dy by dx scenario and turning it 90 degrees. So I'm going to find out what x is, and then I'm going to differentiate x with respect to theta, and then set that equal to 0. Because you can see what I'm saying here. dx by d theta has a minimum at this point here. Set that equal to 0. Set dx by d theta equal to 0, and steam ahead from there. So I know, for example, that x equals, I'm given r, but I know that x equals r cosine theta. I then insert r, x equals 1 minus tan theta cos theta. Now, some people tried then differentiating that, but I would suggest it's a good idea always to simplify things before you steam ahead. So of course that simplifies to so yeah, I go from there, differentiate that with respect to theta, set it equal to 0, and that will give you then what the coordinates of A are. The second bit is to find out what the exact area of R is. So this involves integration. Now the integration would be half R squared. That's the integration that you're going to have to do, which equals half R squared was 1 plus tan d theta. So that equals a half 1 plus tan squared theta plus 2 tan theta. Right, I'm going to have to squeeze this in, but you know what I'm saying. Right, now in the past this would have this might have caused students a lot of problems. Actually, I've seen a question paper in the past which had the integral of tan squared theta and caused a lot of problems, but this time round actually most people have actually handled it quite well. What you need to do is say, okay, 1 sec squared theta minus 1. You use a standard ID. And well, do I need to I mean, those cancel out, so you just you're just integrating now sec squared theta plus 2 tan theta. So that becomes half sec is just tan, and that is 2 log sec. Okay, so that's sorry, I made a mistake here. I need to put the square brackets in. And the actual, if I squeeze these in, can you see? Sorry about that. Yep. Right, so the ones disappear, so I'm integrating sec squared theta, which goes to tan, and I'm integrating 2 tan theta, which goes to 2 log sec x. Okay, so that's the second one there is a standard integral at this stage. If you're unsure about it, you can go and say, okay, tan theta equals sine theta over cos theta, and try and integrate that. Right, so if I substitute in for there, that will give me log 2 plus a half. Right, so that's the result of the integration. Now it sort of gives you a bit of the clue what the answer is in the question. It says use calculus to show that the exact area is a half 1 minus log 2. So you've got this result of the integration. Now what happened for some people is they get this and they try and wodge around to try and achieve this here. Now can you see what the problem here is? The problem here is that this is not R. Okay. This is what I'm trying to find, R. Now the integration that you've just done does not give you R. What it does is it gives you this area here. If I draw a line from O to A, okay, it's actually giving you this area here, inside here. So what you're going to have to do is you're going to have to work out this triangle. If I call that arbitrarily B, I need to work out the area of this triangle OAB, and then subtract that from it. So I can tell you, cutting a story short, I can tell you the area of what I've called OAB, the area there is 1. So it becomes 1 minus the previous answer, which was log 2 plus a half. Right, sorry, I've switched to red here. Hopefully that won't cause you too much problems. So that'll give you half minus log 2. So remember what we're trying to get. We're trying to get half 1 minus log 2. So can you see where I need to go from here? That is now half minus a half log 2. And that's what I need. Half 1 minus log 2. Okay, so that's the answer. Right, so this first part, you've given these flight paths of birds. You're told that they're flying at 120 degrees to one another. You determine the value of A. Now, what you need to do here is you need to work out the scalar product, but just for the direction vectors of these two vectors, R1 and R2, I just need the direction vectors. Okay, I won't go into that in too much detail, but if you know how R1 and R2 are formed, hopefully you'll see that's fairly straightforward. In order to work out the angles between them, I just need the actual direct vectors of the vectors on the right hand side, and just ignore the lambda and the mu. So I say A will equal 2A0 and B equals 0, 1, minus 1. Okay, that's all I need. So I'll say, okay, 2A0, carrying out the scalar product, I always prefer it carrying them out as volume column vectors. So that will equal whatever the magnitude of A is, multiplied by magnitude of B is, and cosine 120. So work that out and that will give you what A is. Sorry, it's a bit of an unfortunate, I've used an unfortunate clash of letters here. That A is not that A. A is just that vector, B is just that vector. So what I'm trying to find out here is that A here. So just realise that that A is totally different. That'll just be the magnitude of this here. So then I need to find out the common point. So that's when I would go back to the full scale vector. So I just need to. Well, I should have actually said before that A. Just in case you need to realise, A in the previous one was -2, I think. Yeah, A -2. So I equate that equation to that equation now. So it'll be -1, 5, 2 plus lambda 2. That's -2 now. 0 equals 4 -1, 3 plus mu 0, 1 minus 1. Okay, if that makes any sense. So that'll give you 3 equations now, which you can then solve to find out. Well, 3 equations for 2 unknowns. That's all you need. So that's okay. So for example, you can look at the top one and say, -1 plus 2 mu equals 4, and that'll lead to find lambda. -1 plus 2 lambda equals 4, so therefore lambda equals 5 over 2. And likewise for mu. Okay, so the last bit, or C anyway, can cause you a bit of problems maybe. I should probably give you the answer for the last. The answer for part B, the common point, was I think this one here. So I need to show that a straight line from this point here, where the nest is, down to the car park, given by this plane here. I need to find the shortest distance. Now, this the plane of the car park is 2x minus 3y plus z equals 2. So that can be represented as 2 minus 3, 1 times r equals 2. Well, r equals z, y, and sorry, r equals x, y, z. And that's very much in common with an alternative form for the plane, which is like that, which hopefully you will have seen. Dot product of n r equals 2. So that's equivalent. Well, this is an equivalent form to this, and this is the perpendicular vector to the plane. So perhaps I'm going to keep that onto one side for a moment. If I've got this nest and I've got this plane down here, given by that previous formula here, I need to find the shortest distance from here to here. Now, if I just draw an arbitrary line and find out what the well, probably best if I call it do it in the other direction. If I set an arbitrary state what this line is in an arbitrary form, which it's that vector minus this vector. I should say that this will just be some arbitrary point x, y, z on the plane. So that'll be the previous vector, which is 4, 0, 2. The previous vector up here is 4, 0, 2. So this line will be given 4 minus z, 0, well, just minus y, and 2 minus, if I can differentiate that, 2 minus z. Okay. Now, the point is that there will be a perpendicular here, given by this one here, 2 minus 3, 1. Okay, so that'll be 2 minus 3, 1. This will be this perpendicular vector here. Now, to find, that's the general formula for the distance between this point and the plane. To find the shortest point, I need to find the component of that in the n direction, in the perpendicular direction. Because remember that this is going to meet this plane at the shortest distance where it hits it at a right angle. So here we've got a perpendicular at a right angle. I need to find the component of that vector in this direction. And I do that by finding out the scalar product. So it'll be 4 minus x, 0 minus y, 2 minus z. Well, taken one thing I should have just forgotten to say is that it'll take the component of that in this direction, but I need the unit vector in this direction. So I'll need to take the scalar product of, I mean that's n, isn't it? That was called n previously. I need to find the scalar product of n, but the unit vector n, the unit vector of n. So I'll need to divide it through by 2 squared plus minus 3 squared plus 1. Now if I expand that out, I'll take the numerals first up here. That'll be 4 times 2 plus 0 times minus 3, so that'll just be 0. And then it'll be 2 times 1. Right, am I going to be able to fit this in? And it's going to be minus minus 2x plus 3y minus z all over what we had before, 2 squared plus minus 3 squared plus 1. Right, so if you're okay with that, I can take that away. What I need to realise now is that this end bit here, that is the negative of this plane here. Okay. So what I can do is that I can replace that by minus 2. So it'll be 8 minus 2 have I missed something else here? Just, what have I missed out? Alright, I made a mess. 2 times 1. Yeah, sorry, there should be a plus there, shouldn't there? So there's a plus there, so that's it. So that's right, 8 plus 2, and that's minus 2, okay? That's minus the 2 that comes from here. Right, sorry about that. Hopefully that's right this time. 8. Yeah. Okay, I think that's right. Anyway, if not, you'll no doubt be able to pull me up on that. And the actual answer to that, for what it's worth, is 414 over root 7. Right, okay. As always, thanks very much if you're still with me at this late stage. There's the so I just repeated the www.maca. Okay. Yeah. If you want to get full scale model answers for this particular paper, go to Maca. As I say, where you may be able to get the exam papers as well. It gives the links to the exam papers. It's just that sometimes there's a copyright on these exam papers if they are too recent. But otherwise, you could go to my YouTube channel, where hopefully there might be 1 or 2 things in there that might interest you as well. So anyway, thanks very much and cheers for now.